We've seen some examples of how series work, how to construct them, how to evaluate the partial sums, and now we're going to go ahead and look at a particular kind of infinite series that's probably going to be the most powerful one that we'll use, and it's going to be like our very base case. That's called the geometric series. So let's go ahead and jump into it. So we have a particular form of a series here. We're going to look at this one here. The series, as we're going to sum from n equals 1 to infinity, 3 times 1/2 to the n. So let's go ahead and make note of what our an here is. That's this thing in the yellow highlight as before. So let's make a note of that our rule an is 3 times 1/2 to the n. Okay. Notice that we are multiplying each term by 1/2 to get the next term. So we want to find the first four partial sums. Now, remember that the first partial sum is just simply the first term. So S1 is just the first term, which in this case is just 3 over 2 when we plug in n equals 1. Now, the second partial sum, S2, that's the sum of the first two terms, but you can also write that as the first partial sum plus the next term. So we have 3 over 2 plus, when we plug in n equals 2 here, we get 3 times 1/2 squared. So that's 3/4. And we do the work there, and that's 9 over 4. Now for s equals s3, okay, for a third partial sum, that's the second partial sum plus the third term. So we go ahead and follow our pattern from before. So the previous partial sum, 9 over 4, plus the next term. Next term is 3 over 8. Okay, 2 cubed is 8. We do work there. That is 21 over 8. And finally, the fourth partial sum, as before. And I just realized I made a small mistake here. So the fourth partial sum is third partial sum plus the fourth term. So we have 21 over 8 plus what happens when we plug in n equals 4? Well, 2 to the fourth is 16. We get 3 over 16 here. And our fourth partial sum is 45 over 16. Okay, so those are our first four partial sums. Now, you may be able to deduce a pattern. Note that each next partial sum has a power of 2 in the denominator. Okay, but now we want to try to find a formula for the nth partial sum. Okay, so let's be a little clever here. Let's go ahead and take our series here. We're going to truncate it, and I'm actually going to relabel this so that the variable of summation here is instead of n is going to be k, so that way we can be consistent with our labeling here of Sn. So let's write the following here. Let's write, say, Sk is the sum from, I got my letters mixed around. Okay, and let's go ahead and make sure my erasers are the right size. There we go. So Sn rather, is going to be the sum from k equals 1 to n of 3 times 1/2 to the kth power. Okay, notice that all we've done here is I've just relabeled the variable of summation here from n to k. I'm allowed to do that. Okay, well, let's go ahead and write out what this actually is. Okay, well, when we expand this, we have, well, 3 over 2 plus 3 over 4 plus 3 over 8 plus 3 over 16. Okay, and we continue all the way to when k equals n. That's going to be 3 over 2 to the n. I'm just going to go ahead and keep it like that. Now, notice that I'm just multiplying the previous term by 1/2 to get the next term. So, in order to maybe do some clever cancellation, I'm going to go ahead and take this expression for Sn and multiply it by 1/2. Okay, so if I multiply that expression for Sn by 1/2, well, I can multiply the 1/2 through inside the sum, because sums are linear, just like integrals. Well, integrals come from sums, so they behave the same way. I'm just going to multiply it through. So let's go ahead and write this out in slow motion here. So I'm going to go ahead and write this out here. And because this guy here is independent of k, I can go ahead and push it inside the sum. So we're going to go ahead and write the following. Okay, k equals 1 to n of 3 2d, well, 1/2 times 1/2 to the k. Well, that's 1/2 to the k plus 1. So what happens is now every term from Sn gets shifted over one space. So we'll have, now the sum starts at 3 over 4, then 3 over 8, 3 over 16, and it continues 3 over 2 to the n, and then the last term now, when k is equal to n, well, the power now is n plus 1, so we have 3 over 2 to the n plus 1. And now take a look here, okay? Take a look and notice that I have this 3/4 here. That's in both of them. 3/8 is in both. 3 over 16 is in both. In fact, every one of those is in there, right? So notice what we have here. We're going to do something very clever. If we subtract the top minus the bottom here, so we do Sn minus 1/2 Sn, okay, if we do this here, okay, we're rediscovering the formula here. What do we get? Well, on the left-hand side, we'll get Sn minus 1/2 Sn. Well, I can factor out an Sn, okay? So let's write it out slowly, okay? We have Sn minus 1/2 Sn. Well, if I combine like terms, that's 1/2 Sn, okay? But on the right, let's go ahead and take a look at what cancels here, okay? On the right-hand side, I'm doing top minus the bottom, so the 3/4 will drop, the 3/8 will drop, 3/16 will drop, everything there drops. And then what am I left with? The first term from the first one, that's 3 over 2, minus the last term from the last one, okay? So what remains there is 3 over 2 to the n plus 1. Okay, but now I have to go ahead and solve for Sn. So let's go ahead and box this thing in green is what we have here. If I multiply both sides of that by 2 to get Sn by itself, we will see that Sn is equal to 3 minus 3 over 2 to the n, okay? Let's go ahead and fix that. And that right there is my formula for my nth partial sum. Okay, this is a very clever way of getting this formula for a finite geometric series, okay? The idea is that you can go ahead and multiply the expression for the nth partial sum by this common ratio, this multiplier, which we're going to call r soon, okay? And that shifts everything over one space, and then you see that you have this nice cancellation. So we have this expression for the nth partial sum. Now, the main question now is, does this series converge or diverge? Well, we're going to have to answer this question here. So remember, okay, a series converges, okay, that's our defining word here, if the sequence Sn of partial sums converges. And how do we figure out this convergence stuff? Well, we just take limits, okay? So we're going to go ahead and take the limit here as n goes to infinity of Sn, and we figured out what Sn was. That's our nth partial sum from above, right there in that blue box. So we'll have the limit here as n approaches infinity of 3 minus 3 over 2 to the n. Let's go ahead and fix that real quick. All right. Now, think about it, okay? Think about that last term there. We have 3 over 2 to the n. As n gets large, 2 to the n is large, and I'm dividing a number by a very, very big number. So I get a very, very small number, okay? Think about it from calculus 1. Okay, that last term goes to 0, so the limit here is 3. Okay, so because that this limit exists, we say that the sequence of partial sums is convergent, and therefore the series converges. So we say that the series converges, and we deduce that the value of this sum is 3. So that's a very powerful thing right there. Okay, we started with this complicated looking thing, and we actually got a number out of it. So we're looking at a case where I can add up infinitely many things and get a finite number at the end. That's very powerful. Okay, so this is an example of, again, what is called a geometric series. Let's go ahead and put that here. This is an example of a geometric series. Okay, a geometric series will take two forms, but they're basically the same up to an index shift. Okay, you need something that looks like an exponential type function. What does that mean? Well, a geometric series will take the form of the sum from n equals 1 to infinity of a times r to the n, or if you want, you can write it starting at n equals 0 as a times r to the n minus 1, or really just a times r to the n. Same thing. Okay, so a times r to the n. You can do it either way. Okay, so this is our geometric series, and we're actually going to be using this, okay? So we're going to determine if the following series are convergent or divergent. And the trick here is that all of these here are geometric series. And I will leave it as an exercise, but you can actually discover this for your own, okay? So if we take our geometric series from before, okay, our base form here, our geometric series, we have the sum from n equals 0 to infinity of a times r to the n, okay? This converges to a over 1 minus r if and only if this r in absolute value is less than 1. Okay, so this is very important. Let's go ahead and put that in a nice orange box here. Okay, that's the only thing that we have for convergence there, okay? That r, that common ratio, that multiplier, okay, that has to be less than 1 in absolute value. So you want to think about it like this. Those terms will shrink in size, and we'll soon learn this in the divergence test, okay, that these terms have to go to 0 quickly enough. Okay, it's not enough for the terms to go to 0, but they have to go to 0 quickly enough, and that's what this exponential factor does. These decay so quickly that we can actually get a limit out of this. So now we're going to determine, okay, and let's just write this here, okay. Okay, that is converges if and only if that happens, okay. So if and only if our common ratio is less than 1 in an absolute value, so 1/2, 2/3, even negative 4 over 15, okay, those are all numbers whose absolute values are less than 1, okay, but can't be 0. Actually, it could be 0 because then we're just summing a bunch of zeros. But, 0 is the boring case. It can't be 1. It can't be minus 1. We need that condition to hold. So now let's take a look to see if any of these series are convergent or divergent. So let's look at this first one here. We have 4 plus 8 over 5 plus 16 over 25 plus 32 over 125. You think you can see the next term? Well, let's look at the patterns here, okay? Well, my denominators here, okay, remember that 4 is the same as 4 over 1, okay? My denominators are powers of 5, okay? 1 times 5 is 5, 5 times 5 is 25, 25 times 5 is 125, so the next denominator should be 625. What's the next numerator? Well, the numerators, how are they going up? Well, we have 4 to 8. Well, 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So the numerators double. Okay, so let's look at our pattern here. Let's try to see what we can write for a sum here. So if I index the sum starting at, say, n equals 0, you can index it at n equals 1 if you like, okay? But just got to be a little careful, okay? So indexing this from 0, we start at 4. And what's my common ratio? Well, my common ratio here, okay, notice that from 4 over 1 to 8 over 5, I have to multiply by 2 over 5, okay? And then I multiply again by 2 over 5 to get 16 over 25. So my common ratio here, r, is 2 over 5. So that is going to be the base of my exponent. That's going to be the base here. And then I'm going to raise this to the nth power here. And if you plug in n values here, you'll see that we get the same pattern here, okay? N equals 0 gives us 2/5 to the 0, which is 1. 1 times 4 is 4. Okay, then to the first power, 4 times 2 over 5 is 8 over 5, and so on. So let's make some identifications here. What are our A and R? Well, here, A is 4, and R is 2 over 5. Now we have to ask ourselves, does this condition hold? Does the common ratio have absolute value less than 1? Well, yes. Okay, 2/5 in absolute value is indeed less than 1. 2/5 is smaller than 1. So this sum converges. Okay, but what does it converge to? Well, let's first make a note here. This is convergent. Okay. And so how do we find the sum? Well, we apply our formula here in the orange box. Okay, so we have the first term, which is a, 4, over 1 minus the common ratio, 1 minus 2 over 5. Okay, if we do a bit of arithmetic here, we have 4 over, well, 1 minus 2 over 5 is 3 over 5. Okay, and then do some fraction division. We get a sum of 20 over 3. That is the sum of this series here. Okay, so notice how we deduced what the pattern was, set it up from everything in the orange box there, and we've gone ahead and figured out what the sum was. Excellent. So now let's take a look at this one here. Negative 3 to the n minus 1 over 4 to the n. This might be deceiving because it doesn't look like it's a geometric series, but actually it is, okay? Let's go ahead and use some exponent rules here, okay? Notice here that my exponents here don't match. I don't have an n or an n minus 1 on both. The numerator has an n minus 1 in the exponent, and the denominator has an n. But we can fix that very easily here, okay? What I'm going to do is I'm going to instead write this 4 to the n as the following. To start the sum at n equals 1, we have negative 3 to the n minus 1. And to write this 4 to the n is something very clever here. I'm going to write this as 4 times 4 to the n minus 1. Now, why did I do that? Well, now if you take a look here, my exponents match. Okay, and now I'm going to use a property of exponents here. If I have a quotient of things, each of which has the same exponent, then I can go ahead and cram them into one thing, have that as a power of a quotient. So what does that mean? So we have this sum from n equals 1 to infinity. Okay, we have negative 3 over 4. That's all going to get raised to the n minus 1 power, but then what about that extra 4 in the denominator? That's a 1/4. All right, now let's make some identifications here, okay? Our first term, our a, our initial value is 1 over 4. Okay, that's the a coefficient there, and the r here is negative 3 over 4. Now, some of you may be thinking, Sean, you said the formula had to have an n in the exponent. Well, yes, but you can also write it as follows, okay? You can also write it like this, okay? This here, you can also write it as the sum from n equals 1 to infinity of a times r to the n minus 1, and the formula still holds. First term divided by 1 minus common ratio, okay? In fact, you can check that you'll actually generate the same sequence of terms if you just plug in here. Well, what's 1 minus 1? It's 0. You just read next. So, now let's take a look at our condition. Does our common ratio have absolute value less than 1? Well, negative 3/4 has absolute value, 3/4, which is indeed less than 1. So this thing converges. And so, its sum, well, we just use our formula here. First term, which is a, that's 1/4, divided by 1 minus r. Be very careful. Okay, you do some work here on the bottom. 1 minus a minus 3 over 4, minus minus is plus, so you get a 7 over 4 there. Okay, and if you do some fraction work here, you get a sum of 1 over 7. Nice how that works out, huh? All right, let's take a look at this last one. Okay, again, doesn't look like a geometric series, but we can make it if we remember our exponent rules, okay? 3 to the minus n times 8 to the n plus 1. We have a negative exponent, so let's go ahead and write it as a fraction, a sum from n equals 1 to infinity. Okay, 8 to the n plus 1, and then over 3 to the n. Something looks a little fishy here. See if you can spot it. Okay. Now, what I'm going to do is the following here. I have an n plus 1 and I have an n. My exponents don't match. So I'm going to peel away from the top here just by using my properties of exponents. We have 8 times 8 to the n over 3 to the n. Okay. Now I have the same thing as before, right? I have a quotient of things that have the same exponents. Okay, save for that extra 8 there. So I can go ahead and write this as follows. I can write this as 8 times 8/3 to the nth power. Now this is still a geometric series here. Okay, let's make some identifications here. In this case, a is equal to 8, And R, the base here, okay, the base here, the multiplier is 8 over 3. But 8 over 3 is slightly less than 3, which is certainly not less than 1. This is bigger than 1 in absolute value. So this thing diverges. Okay, so because the common ratio is bigger than 1 in absolute value, this sum does not diverge, and hence it does not have a sum. The sequence of partial sums does not converge. Okay, so we've seen how to use a very special series, okay? This is a very classic type of series that will appear, and it's going to be one of our baseline ones, okay? Later on, when we talk about the ratio test, okay, you'll see that this is going to come back up, right? We're basically going to compare it to something like this, okay? Now, why is this helpful? Okay, because this can actually give us something nice when we talk about power series expansions in chapter 6. Okay, and this is an example of one class of convergence of series that can possibly converge here. Remember, that common ratio has got to be less than 1. Okay, we're going to go ahead and take a look at some more series, another type of series that you may have to do some algebra stuff for. I wonder what that could be. I'll see you in the next one.